Hello, look at this. I got myself a spectrum analyzer. This is a Hewlett-Packard 8590A 10 kHz to 1.5 GHz instrument. It is quite old, about 30 years old I guess, and it's not working properly. I got it on eBay for $180 plus almost $50 for shipping and handling. Not bad at all, especially if I can fix it. It seems to be in a decent shape cosmetically. The rubber bumpers look a bit worn and there are some scratches on the cover, but the front panel looks nice. And the description was that it doesn't pass self-calibration and the signal looks noisy. Let's power it up. There you go. Looks noisy indeed. And the revision is 9187. With the correction off, the signal looks better. Probably a bit high noise floor. I found some pictures on the internet which show the noise floor one division below, but that might be with correction. So let's try running the self-calibration. To run the calibration, we need to connect the calibration output to the input. Well, looks fine on the first glance. So let's run this first frequency calibration. It's done. Let's go to the next one, amplitude calibration. It's done as well. Yeah, but the result looks even worse than before. Let's check the calibration output signal. Here is the spec. And calibration output must be minus 20 dBm, 299.9 MHz, with second through fourth harmonics greater than minus 60 dBm. So it must have intentionally high harmonic content, and we see that the sine wave is not quite a sine wave, it is distorted because of this high harmonic content. And yes, it is about 300 megahertz, and minus 20 dBm corresponds to about 22 millivolts RMS. And we see here 19 millivolts RMS. Close enough, I think, for the accuracy of the scope. So the calibration signal looks good to me. I tried running the frequency calibration again, and it failed this time with this message, span sense fail. So the calibration indeed fails from time to time at least, and the result looks bad even if it passes. So let's start troubleshooting the thing. Let's have a look inside. I read some documentation, so I already have some idea about what's going on here. The signal goes from the connector on the front panel to this point, which is the input to the programmable attenuator. Then the signal goes into the first converter down there, and it gets up converted to 2.05 gigahertz. This box with the ribbon cable attached to it is the first local oscillator, YIG oscillator, which can be tuned from 2.05 gigahertz to 3.55 gigahertz. And the output of this oscillator is on the front panel, and it would be great to start by checking it, but unfortunately I don't have any means at the moment. Then the signal goes from the first converter through this low pass filter to the second converter, where it is converted to 1.7 gigahertz. Here is a connector to check the second LO, and unfortunately I cannot check that as well. It is 1.7 gigahertz. This is the output from the second converter. It goes to this point, to the second IF. This is the output of the second IF, goes here to the third converter, and at this point the signal should be 321 megahertz, and we can check that. This is the output of the calibrator. This is a band pass filter. This is a step gain. This is another band pass filter. This is a log amplifier. This is the power supply. This is the display module. And this board is analog interface, which has controls of the input attenuator and DAC and driver to control the YIG oscillator, to tune it in that wide range, and maybe something else is on that board. And there is some other block there. I'm not entirely sure what this does. It is sitting between the first LO and the LO input to the first converter. And this is the bottom of the unit. Here we have the main processing board. This is optional GPIB board. This is a video board, the output of which goes to the display module. There are power rail LEDs showing that power rails are probably fine, and I measured them. They look fine to me. There are 16 LEDs here on the main board, with explanation over here, and these two, which are on, are not used, and they should be on during normal operation. The rest are off, as they should be, so no problems here. Check this out. I managed to borrow this wonderful instrument from a friend. This is Agilent E4404B spectrum analyzer. It can go up to 6.7 gigahertz. With this guy we should be able to check everything. Let's start checking from the first LO, and because there is a warning here, 0 volt DC max on the input, just like on this analyzer, I want to be super careful and check before connecting. There should be no DC here at all, but let's make sure. There you go, no problem at all. So we should see on the first low output from 2.05 to 3.55 gigahertz plus 10 dBm. Now let's set this analyzer amplitude slightly higher, 15 dBm let's say, and the frequency range slightly wider than we need. Let's start from 1.5 gig and stop at, let's say, 3.8 gig. And now we can connect the first low. And there you go, it's jumping around because the analyzer is sweeping all the way across this range. We can stop that by setting 0 span. So now it stays put. We can do peak search at 2.8 gigahertz, about 11.5 dBm, looks fine. So now we should be able to tune here up and down and up. Looks fine, and we can set this peak search to follow this continuous peak on. Looks good. Let's go to the minimum, 10 kilohertz here. Alright, 2.052 gigahertz, around 10 dBm, looks great. So let's go to the maximum, 1.5 gig, and we see what we should, 3.547 gigahertz, about 10 dBm, looks great. So it seems to me that the first low output is fine, which means that YIG oscillator is probably okay, and its driver on the analog interface board is also fine. Let's check the second low right here. I have this small cable. Let's connect the analyzer and have a look. A quick DC check again, just in case. Here it is, 1.7284 gig, about minus 11 dBm. It should be 1.7287 plus minus half a megahertz, so it is within spec. The amplitude is not mentioned, unfortunately. So let's assume the second low is fine. After playing with the analyzer some more and reading more of the documentation, I'm starting to suspect the first converter, or more specifically the mixer in the first converter. First of all, these calibration signals we see are jumping around, and I've seen the noise floor also moving up and down by a division or so. And this main tone right now is lower by about 10 dB. It should be minus 20 dBm, and now it's about minus 30 dBm. This could be because of calibration is not done right, and if we turn the corrections off, the signals go even lower. And I don't think this much of a correction is normal. So this main tone should be corrected by about 15 dB or so. And I also don't like that we don't see the second and fourth harmonics. This is the main tone, 300 megahertz. This is 900 megahertz, third harmonic, and we should see the second in between, 600 megahertz, and we should see the fourth, 1200, just like on this example here. And I think I've seen that before, and the reason might be that they are below the noise floor right now. Another piece of evidence is the calibration data. We can look at it here, and there is some explanation in the manual, and this description here is saying check the cal data display to see if the DAC settings are in the correct ranges. Our L-Venner column from 200 something at the top to single or low double digits at the low end. And in this example they show this column runs from 213 down to 3. And what do we have? We have from 255, which is the limit, I believe, and it runs down to 157, not even to double-digit numbers. And here, just above, they say if the level on the analyzer is wrong and all three LOs are fine, then the first mixer diodes probably have been degraded. And here, in the troubleshooting hints for the first converter, they say the most common first converter problem is damage to the mixer diode. The usual symptom is 10 to 14 dB loss of sensitivity. Let's check this first converter. I unbolted and lifted up this RF section. Here is the first converter. This is the input. This is the output. This is the low input and the low output to the front panel. So I'm going to disconnect the input and the output and connect a signal generator to the input and the spectrum analyzer to the output. Here we are. This is the output of the first converter with the analyzer and the test set to 0 frequency, 0 span. So what we see is the low feed through, and I think it's a bit too high, about -5 dBm, but I'm not entirely sure what it should be. Now let's connect this 10 MHz -10 dBm signal to the input, and we should see it up converted. There you go. We see these two up converted signals, and if we move the peak search, -36 dBm, and I think it's way too low. I would imagine a conversion loss of about 10 dB or so from these -10 dBm. So I would expect something around -20 dBm, but we are getting -36. So it seems to me that we have that described symptom of 10 to 14 dB loss of sensitivity of the first converter. Here is the first converter. Removed all the bolts. And there you go. There is a description of this converter in the service manual. Let's have a closer look at it. This point is the LO input, and these two traces and two resistors form a power splitter. This side of the power splitter is the LO output to the front panel, and this side is connected through this rigid coax to the mixer, which is a balanced 2-diode mixer. The center conductor is connected to this diode and the shield to this diode. The RF signal comes in here and goes through this 1.55 GHz low pass filter to the mixer. The output of the mixer is under this polyiron block. There are two traces to this 6 dB pad, and output of that goes through this 5 GHz low pass filter to the output connector. And this block of polyiron somehow helps to absorb harmonics and such, as they say. It's the same material as in here. So now I'm reasonably certain that this converter is dead, so I would like to try fixing it. Unfortunately, there is very little information about these mixer diodes. The marking on them seems to be like so, HP010385, and the service manual mentions them as a matched pair and says that they must be replaced as a set. And there is a part number for the set, and of course it's not available anywhere nowadays. So I thought I could try just regular RF Schottky diodes like 1N5711 or something like that, but after some research I believe there is a better way. I found these surface mount RF Schottky diodes from Avago Technologies, which is Broadcom now. They exist in many different configurations. We want this series configuration, and here they say that dice found in pairs and quads are taken from adjacent sites on the wafer, assuring the highest degree of match. That's exactly what we want. There are 3 families here, and they differ by breakdown voltage: 75 volts, 25 and 15. The junction capacitance: 1.6 picofarad, 1.1 and 0.7, and the series resistance: 30 ohms, 10 and 6. Higher breakdown voltage goes at the expense of higher capacitance and higher resistance. I bought a few of these, but now I regret I didn't buy a few of these as well. They might be a better match for this application. They are not very expensive, about 90 cents a piece. Here they are. Let's give them a try. Here we have the diodes desoldered from the board, and they seem to be crimped into these standoffs, so I removed them together with the standoffs. I really hope I'm not disturbing the RF magic too much by doing this. It was difficult to test them in circuit because this side appears to be shorted there. So let's test them. This diode appears to be open, and this one appears to be shorted. So it is confirmed they are dead. Here is the result of careful soldering. Check it out. It looks like a successful fix to me. The low feed-through is much lower, about minus 24 dBm. It was about minus 5 before, and the up-converted signal is about minus 27 dBm, which is lower than I expected, but I'm not so sure now. I remember the 6 dB pad in the converter, so maybe this is fine given the minus 10 dBm input. But now I regret even more not buying the diodes from this family with much lower series resistance and lower capacitance, and I think that 25 volts of breakdown voltage should be fine, because the maximum input signal to the analyzer is 30 dBm, which is 20 volts peak to peak. So even if all that power gets into the converter somehow, with no attenuation, which should never happen, it is still below the limit. Maybe I will buy these diodes later and put them in, but I need to return this wonderful analyzer soon, so I'm not sure when and how I will be able to evaluate that result. But for now, let's see if the analyzer is gonna work with the fixed converter. It passes self-calibration now, and the result looks good on the first glance, except that the second and fourth harmonics look a bit too low. Let's have a look at the calibration data. This column looks closer to what was suggested in the service manual. Still does not go as low as single digits, but certainly looks better. This is a 1 GHz 0 dBm signal from my adjuvant signal generator, and it looks great. The amplitude is shown here, 1.7 dBm or so, quite close. Let's try minus 10 dBm. We see minus 9.8 or so, looks good. Let's try minus 20, and we see minus 21 or so. Let's try minus 40. It's a bit low now, minus 43.7 or so. Let's try minus 60. It's a bit lower again, about minus 65. Perhaps some adjustments are needed, but overall looks good. I think I can call it a successful repair. I hope you enjoyed this video. Thank you very much for watching. Bye.